Greetings, Earthlings. Today we're taking a look at the graphics card for the Nova 445. You can see it here installed. I've been trying to work out the problem why it won't initialize. You'll see here, let me show that. I did PC boards, once again, JLC PCB. I went with the black color this time just to try it. And I was hoping for like a wicked piss high gloss black. And it's not that. In fact, it's more of just a dark green. So, not what I hoped for, but beggars can't be choosers, I guess. I don't know. The cutout here, you can see that this is the processor chip, which reportedly runs hot, and then this is the front panel board or front panel connector or whatever, so I needed to leave room for those. And then there's this resistor here, which acts as a current source for the integrated injection logic, which is the technology used in that processor, and that sticks up. So I needed to leave room there for some airflow and to be able to get things in and out. So that explains the cutout. And of course, I didn't need all the space on this board anyway. I'm not going to fire up the logic analyzer or its built-in world's worst oscilloscope. I'll just tell you what the problem is that I've discovered. I'm okay talking to the board. Again, this is Nova instruction set, Data General Nova, and it has an I/O subsystem. So I talk to the chip, the processor chip. Oh, well, first of all, wait. The processor chip, that's a Zilog Z7220. Zilog, which is actually an NEC design that Zilog licensed. I think Intel licensed them as well. I don't remember the Intel chip. But I was able to find the Zilog chips for cheap. If you buy the NEC parts, they tend to be rather expensive. But nobody seems to know what the Zilog chips are, so they're available fairly cheap. Maybe not anymore. Once I've bought a bunch of them and done this video, now there's going to be a run on them. But anyway, I've got as many as I need. The chip, and basically there's the chip, there's a clocking circuit, there's interface circuitry, and there's no RAM on the board. It uses the dual port RAM, which is on the main processor board. And then there's a video output driver stuff over here. So that's the whole board. The chip looks like an I/O device to the processor. So I talk to it with the I/O instructions, data out A, data out B, data in A, data in B, and so on. That part is working. That is, I'm decoding those instructions correctly and putting the right signals onto the processor chip. It's got a standard read-write and then an address bit to say, well, so there's two places you could write and there's two places you could read from. Okay, so we map that into two separate instructions, two separate ports, if you will. Data out A, data out B, data in A, data in B. So the AB translates to that address bit, and the data out translates to a write, and the data in translates to a read. That all seems to be working. However, I made the same mistake that I made, if you recall, if you've seen the previous videos, with the ROM code, or the ROM, or they're actually flash chips, but EPROMs they could be, or whatever. Anyway, I reversed the bits. So if we look here, and I don't know if you can see this, the Nova and this Fairchild chip uses bit 0 as the high order bit of a word or a byte. Intel, NEC, most of the microcomputer world uses 0 as the least significant. So what I did is I mapped, it's called DB0 on this chip, data bus 0, to IBI 0 on the on my board, which is information bus inverted. Okay, it's buffered and inverted and stuff, but basically it goes straight to the processor. So instead of mapping the low byte, I mapped it to the high byte and with the bits reversed. So I'm going to have to fix that. Once again, there are multiple ways to fix that. I could do it in software, or I could do it in hardware. This time, I think I'm going to do it in hardware. I'm going to modify the board because I want the instructions, the code, to sort of match what you see in the data sheet in terms of the bit order and stuff like that. If you look at the status byte or the instruction values, the command values, well, in the case of, say, the command and parameter values, I could either pre-reverse those and build it into the code that way, in which case the code would look funny, or I could add instructions to swap all the bits around, and that would make the code look funny. I'm not worried about the extra overhead of doing the swapping, but just that it's sloppy. So what I'm going to do instead is, and I don't know if you can see these, but it's these lines right here that come over to this connector. And so they just need to be cut and moved to different points on that connector. So we'll do that and try again and see if it initializes properly. Okay, so here I am ready to make the mods. Now I've removed the chip from the board because that's an NMOS chip and I don't want to be blowing it up. And nothing else on here is static sensitive. This is all TTL. But I was a little concerned about that. Not that I need to be too concerned because I do seem to have a few spares. Now, if you were paying attention earlier, I mentioned that this connects to IBI 0 through whatever, or 15, and that's information bus inverted. And then if you looked at the data sheet for the 7220, you would see that, well, it's not inverted. So maybe there's another problem. But no, I don't think so, because, yes, mass confusion. The IBI is actually active high. On the processor chip, there's an information bus, which is active low. So that gets inverted to IBI, which is now active high, it probably should be called double inverted or not inverted or something. Well, yeah, that's confusing. Okay, swell. Okay, we're looking here at the connector. I left my little red pointer in the other room. And we have this here. This is the I/O connector, which is this one here. And IB0 through IB7 are there. IB8 through 15 are there. So I'm going to take 0, that goes to 15, 1 goes to 14, and so on. And it turns out that the only place that gets connected to is the processor chip itself. Well, you can see that if you can see the traces here. They just come straight over here to the chip. There's nothing coming out the other side. So I don't have to worry about any other things. So what I'm going to do is I'm going to cut these traces, and then I'm going to solder little blue wires, you see, from there to there sort of deal. I'm just trying to figure out where to cut them right now, to make this easiest, I think I'll cut them right along here so that I have, can you see that? Can you see that? So they're traveling in this direction here. If I cut them here, then I can solder onto here and come across this way. Cutting them, oh, and there's one here that I don't want to cut. So there's 8 of them that I do not need to cut. Cutting them involves the use of sharp tools. Well, this is not very sharp. This is what's commonly called a Swiss Army knife. And another way to do it is with the sharp point of some diagonal cutters. But I'm going to start with try it with the knife here. Just go straight across. Whoops. And again, try not to get that one. So I'll do it this way. All right. Sure this is making for a great video here. Okay, I believe that's scraped. I'm going to check that. Continuity tester here. Just to see if I got them all. Where would that go to? It should have been that one. Seems good. It seems good. Seems good. Okay, so I believe I have those disconnected. Now I'm going to scrape away the copper here so I have something to solder, or not the copper, the solder mask. So I have some bare copper to solder to. That looks pretty good. I'm going to get some flux. Okay, I'm going to wipe those with this flux pen. I'm just going to wipe some flux on there to hopefully make connecting a little easier. And now we'll fashion some little blue wires. So I think this is instructive to go through this. You know, if I had breadboard, I could have breadboarded this circuit on, you know, those plug-in breadboards, and then I would have made this same mistake, and it would have been real easy to fix. I just would have jumpered the wires around. I find that, you know, you get to at least 90% just laying out the PC board. You may well make some mistakes, but they're easy to fix. And this is the important thing. You don't have to worry about you know, making mistakes, because you can fix them. Don't be embarrassed by them. Everybody makes them. I mean, if I were doing this for a living, I'd probably be fired, because this is the second time I've made this same mistake. But I'm not. And I'll go and update the schematics and the PC board layout. So should I do another board, you know, if I find enough mistakes, I'll do another run of the boards. But otherwise, it's no big deal to have some mods on the boards. If you look at professional boards from, you know, real companies, you'll see quite often lots of little corrections, additions, and what have you. So I guess the whole point of that was to say, don't be afraid to, you know, to do it. If you're reluctant to go down that route of making printed circuit boards because you're afraid, you're going to make mistakes, and then it'll cost you more money or whatever because you'll have to redo the boards. No, it's just going to cost you some time, and it's really not much different than, again, than if you were using a breadboard. So this one, okay, so on the connector, this one went to the second pin in here on this side, and I am going to connect it to the second pin in from this side. So that'll be easy enough to do, I think. To get it approximately the right length, that's going to go there and over to there and about yay long. About yay long. I think I made that a little too long. This is just going to wrap around that pin, and then we'll solder it. And because there is a gap, there is some airspace, if you will, between the connector that this plugs into and the boards, so I don't have to worry about losing that space or something. Tweezers come in handy from time to time. Okay. Now to solder this end, what I've done is I've laid it down flat against that place where I scraped off the trace. The flux is right now, well, this is holding it down, but the flux is also holding it in place a little bit. It's kind of sticky. And hopefully, when I lay the heat on it, it'll stay in place. Some solder, whoops. Didn't. There we go. Okay, that's a decent enough connection. All right, and here's the finished product. Doesn't look all that pretty, but it doesn't need to. I cleaned up the flux with some alcohol, 99% isopropyl alcohol right there. Wow, look at that. One little thing to check. First, I want to check that I don't have two adjacent pins shorted. Okay, that's okay on that end. Take those off. Okay. Now let's make sure that we have some sort of connection there. That's connected to there. That's connected to the next one. That's connected. Okay. That looks good for now. We'll get the chip back in it and take it back and fire it up. See what happens. Let the smoke out. Okay, so here we are. It's all hooked back up. And we'll see if it initializes. Now, what I'm checking here is pins, what is it? 3 and 4. Oh, no. That's my flaky power strip again. The horizontal and vertical sync outputs from this processor chip, which are pins 3 and 4, and I'm expecting to see some pulses on those if it gets initialized correctly. And so let's power this up. And start it. Oops, I'm not sure that started. Okay. And the scope, I've only got the one probe right now. There's pin 3, which should be the, I think that's the horizontal pulse. No, let's go there. And let's try pin 4, which should be the vertical sync, which is much, it's like a 60th of a second. There are the vertical sync pulses, so go 500 microseconds. Okay, those are my vertical sync pulses. And those are my horizontal sync pulses. It looks a little weird, but I am getting pulses. Okay, there's some weird aliasing going on there or something. Yeah. Okay, so that's as far as I had hoped to get today, so I will proceed and figure out what I have to do next.